Hello, students. So, in our today's class, we will study about indices and exponential functions, and our scope of discussion would be based on the curriculum for grade 9. So, obviously, there would be things which are for higher grade, and we would intentionally keep them out of our scope of discussion. And so, let's get started with our journey on indices and exponential functions. Okay, so you might be wondering why I have chosen, two names in the nomenclature, indices and exponential functions. Yes, we would get to both of them. We would understand what do we mean by indices and then why I have given a slash exponential function in the nomenclature itself. So let's get started. So students, in mathematics, a recursive function a recursive function or a repeated operation is very common by nature. So for example, right from your childhood, you had studied, say if I ask you 2 plus 2 plus 2 plus 2 equals to how much. So if I ask a grade 1 student, he or she would say 8. And maybe if he or she has also learned multiplications, he would say it's actually 2 into 4 equals to 8, right? And we had studied that this second expression which we have written here, which is nothing but multiplication or the product function, that is nothing but product or multiplication is a repetitive or recursive addition, right? So it's a recursive addition, right? So similarly, as product or multiplication function is a recursive addition, similarly, if I replace all these plus signs by say multiplication signs, so my intention is to know what is 2 into 2 into 2 into 2. So I'm multiplying 2 4 times with itself, right? So obviously it will not be 8. So we need to see what will be the value. And we know that this is nothing but 16, right? So our basic method is we multiply 2 with itself 4 times and we say it as 16. Now, if I want to if I want to express it as indices or an exponential function, so let us see how do we define that in mathematics. So in mathematics, it's defined as that we write 2, which is called as the base, okay, and we write a superscript. And what is a superscript? The superscript is how many times it is multiplied. So here it is multiplied 4 times, so I'll write 4 as a superscript. And obviously here this 4 is called the index, right? And obviously the answer is 2 to the power 4. So rather than writing 2 into 2 into 2 into 2 4 times, the shortened mathematical notation for that is 2, which is the base, raised to the index or power. So people say index or power, and whatever we get, that's our, the value, that is 16, right? So that's why obviously in today's class, we will study about the properties of when a particular base is raised to a particular index or it is multiplied some n number of times with each with itself. What does it produce as a result? So that is why today's study we will call it as indices. Also, because it's a mathematical function and we would get into the graph part of that also a little later. So that's why we'll call it an exponential function. Okay, but then please note down this basic definition that 2 to the power 4 is nothing but 2. So it is read as 2 to the power 4. That is the most common, way of reading it out. And obviously, how we find it out? We multiply 2 multiplied with itself some 4 times. Okay, so base is multiplied index number of times or power number of times with itself, and that function is called as an index function or an exponential function, right? Now, we started with a constant. Now, is it defined only for constants? Obviously, the answer is no. So let us extrapolate it to the general rule, and let us understand how we can, rewrite it. So it is defined as a. So suppose, I can define a to the power n. So as we have already understood, a is the base, n is the index or power. So a to the power n is defined as a multiplied with a multiplied with a. How many times? Yes, n times, right? And obviously, one interesting thing here is to notice n belongs to n set. So which means obviously your n is greater than or equal to 1. Okay, and fundamentally we normally take it as, n greater than 1. Why I removed plus, equal to 1, I'll just tell you in few minutes. Okay, so for all natural numbers, or when n is greater than or equal to 1, a to the power n is defined as a into a into a into a n number of times. Okay, so that is nothing but our index or indice, your exponential functions. Okay, now you can write it down as your first rule that a to the power n is nothing but a multiplied with it n number of times. Okay, now let us understand why do we have this restriction in place, right? And from there we would understand few other rules of indices which would be used in, doing the various mathematical modeling and, physical modeling, problem solving. Okay, so for example, if if now one more thing is, this can be a constant or a variable, so there is no restriction on that. Similarly, this can also be a constant or a variable based on the given problem with no restriction. Yeah, there is one restriction, that this n should ideally be greater than or equal to 1. Okay, so for example, if I'm saying 1.2 to the power 5, obviously what does it mean? Very simple. 1.2 into 1.2 into 1.2 into 1.2 into 1.2 5 times. So we multiply 1.5 1.25 times with itself, and we get 1.2 to raised to the power 5. Okay, very simple. So no, we don't have a restriction there, as long as this n is a natural number, or obviously, it belongs to n set that is greater than or equal to 1. Okay, now for example, if I were having so does this rule change if I have it as, minus suppose 4 to the power 2? The answer is no. So minus 4 to the power 2, as long as your index or, your power is greater than or equal to 1, and it's a natural number, obviously this would be minus 4 into minus 4 as defined in our first and the basic rule related to indices. Okay, so this is the most simplistic thing that we could have done here. Okay, so I hope you have noted it down. So let us now introduce small tweaks into this, problem. Okay, and in today's class we will just introduce the base concept. We will just understand these small tweaks. We'll understand the laws related to indices, and in the following lectures we would go more deep, and we will solve, various problems on indexes, and we will solve various word problem, and which is fundamentally which normally comes up in your any of your IB or Cambridge curriculum. You get, very frequently. Okay, so now for example, now when I would suppose I have 4 to the power 1, what does it mean? Same rule. So 4 multiplied with itself for one time. So multiplying something one time doesn't make any sense, because multiplication operation is defined between two operands, right? So we have always known A into B. If I'm saying I'm multiplying A with itself, then it would at least be A into A. So which means it is two times already, right? So the basic definition says anything raised to the power 1 is that number itself. Okay. So that we can write it as our second rule, that A to the power 1 equals to A. So you can write it as your rule number 2. Okay. That any real number, and here you notice I'm saying where A belongs to your any real number set. Okay, real number set. Any real number raised to the power 1 would be that same real number itself. So which means 4 to the power 1 is how much? 4. If I say 5.2685932 raised to the power 1 is how much? Obviously the same number. Okay. If I say minus 1 by 3.654 raised to the power 1 is how much? Just remove this power and it's the same thing. Okay. So obviously this is our second basic rule which we should understand, that any real number, when it is raised to the power 1, it produces the same number itself. And this is fundamentally by definition. So let us understand this relationship here. Okay. Now, you may note it down. Let me give you a few seconds and I'll sip a bit of water in the meanwhile, and we'll get to the next. Okay, so let's get going. Now, now we have defined it to be greater than or equal to 1, right? So equal to 1, what is the law? We have already explained. Now let us try to understand what happens when your this index is equal to 0. Okay, so now we will understand A to the power 0. Okay, and again this is defined that anything. Okay, so let me write it down first here. So any real number, when it is raised to the power 0, the value is 1. So A to the power 0 equals to 1 for all A not equal to 0. Why? Because 0 to the power 0, the definition of it is beyond the scope of this discussion. So I would leave it for a relatively higher studies discussion. And let us understand that any real number for all A which belongs to R set, and A is not equal to 0. So any real number other than 0, when raised to the power 0, the value is 1. Okay, so you can write it as your rule number 3. So again, some very small questions. So if I say 1 by 3 to the power 0 is how much? 1, right? If I say 56 to the power 0 is how much? Answer will be 1. 3.1254696873450 to the power 0 is how much? 1. Okay, so any real number that is non-zero. But if I say 0 to the power 0, if by chance you come across this, you can still write 1. That's okay. But as I said, with the caveat that this is beyond the scope of this discussion, I would leave it for a higher studies discussion. So any non-zero number raised to the power 0. So for example, if I say minus 3.1256 blah 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 raised to the power 0, again the value would be 1. Okay, so this is our law number 3. So far we have studied three basic laws, that is A to the power n, where n is any number, any natural number greater than or equal to 1. It is defined as A multiplied with itself that many times, and that is written as A to the power n. Then we studied anything to the power 1 equals to the same number, and any non-zero real number when raised to the power 0, it produces 1. Okay, so these are the first three laws that we have understood. Okay, now let us move a little further. Okay, so we have we have not yet gone into what would be the meaning of a to the power minus n. Okay, so when I'm saying 2 to the power 4, obviously we understand that this is nothing but 2 into 2 into 2 into 2, 4 times, right? And we say that the answer is 16. Okay, now if someone says 2 to the power minus 4, so the question is whether this is right or wrong, whether it's defined or not defined. And the answer is yes, this is defined in mathematics. And how it is defined? So you may argue that, sir, how can I multiply 2 with itself minus 4 times? Because obviously we cannot really do any counting in negative numbers. Obviously negative numbers have come up as a mathematical conjugate of the positive number set that we have. Now what is defined is anything raised to the power minus n, where n itself is a your positive integer, is nothing but 1 by a to the power n. Okay, so 2 to the power minus 4 is nothing but 1 by 2 to the power n. So that is 2 to the power 4, because n here was how much? Your 4, you had a minus, and you had a base here. I retained the base. Whatever was the negative power, I put it as 1 by that much, 1 by 2 to the power 4. Now, you may also counter argue. So can we say that 2 to the power 4 is 1 by 2 to the power minus 4? Absolutely right. Absolutely right. Because again, when we have 2 by 2 to the power minus 4, this would further be solved as 1 by 1 by 2 to the power 4. So obviously it would then go to your numerator, and you would end up getting the same thing, 2 to the power 4. So we would use these tricks obviously solve problems related to indexes or indices. And obviously we would see the majority of them in our next lecture. But yes, for understanding the law or understanding the relationship, a to the power minus n, where a could be any constant, a could be any variable. When it is raised to a negative power or negative exponent, then that can be rewritten as 1 by a to the power n. Okay, so we can say this as your law number 4 related to indices. Okay, so take a note of it quickly, and then we would go into the next law in a minute's time. Okay, so I hope you would have already noted it down. So let us move into the next set of laws. Okay, now, so we started with the best case scenario, a to the power n, where n was a positive integer greater than 1. Then we equated it to 1. Then we took it to 0. Then we took it to negative. So what is left? We have still not touched. When I'm saying a to the power n, can this be a fraction? Can this be a fraction? Is it defined or not? Right? So if I'm somebody is saying 3 to the power half, 3 to the power half, as per the basic definition, I should multiply 3 with itself half times, which is very absurd when we talk in terms of logic and your logic and theory, right? So in mathematics, it is defined as a to the power 1 by n is nothing but the nth root of a. Okay, so this is something which you would have studied in radicals and surds. So we would also have we'll take a lecture on that, so you can connect more on that piece. So any real number, any non-zero real number, when it is raised to a power 1 by something, 3 to the power 1 by 2 is nothing but we should retain a, and under the radical sign it is half, so it should be the second root of a. So for second root, we know that we don't really write 2, so I'll just write it as root a. So similarly, if I say 18.2 to the power 1 by 4, what does it mean? So it means very simple. Retain this a, that is 18.2, use your radical sign, and 1 by whatever is there, it should be that much root of this radicand. So we retain the radicand, we use the radical sign, and whatever was in the denominator of that fraction in the index, we took that much root of it. So obviously for mathematical calculations and all, this would not be as easy as your natural numbers. But then yes, let us understand the relationships here, because we would see how to solve problems using these tricks by doing the required conversions in our upcoming lectures. So that's why we can write it down as our next law, that a to the power 1 by n is defined as nth root of a. So probably we can say that this is nothing but our indices law 5. Okay, and again, there is no hard and fast rule that which one we should call indices law 1 and 2. So in whatever logical sequence we are going, I'm just putting them in that sequence. In your book you would probably say it in a different sequence, doesn't matter, but then the concept remains the same, concept doesn't change, right? So yeah, let us move on to the next one while you take a note of it. And then, so far what we have completed is we have completed the basic definition of indices, and from that basic definition of indices we have defined 5 different laws. Now let us go into a little deep and let us see what kind of other laws and other relationships that we can define on indices and that would be of use, right? So for example, as a kid, you started learning natural numbers, you started learning the basic numbers, and then what did you learn? As a kid you started learning additions, subtractions, multiplications, and divisions. So these are the 4 basic mathematical operation on any mathematical operand you have. So let us try to see how we can have similar things related to indices. Okay, so for example, if I'm saying, say, 2 to the power 4 into 2 to the power 3, let us try to solve it. Okay, so when I say 2 to the power 4, what does it mean? I can say this is nothing but 2 into 2 into 2 into 2 4 times, right? This is our law 1, that a to the power n, where n is a positive integer greater than 1, the base is multiplied with itself n number of times. So I multiplied the base 2 with itself 4 times. So this is nothing but 2 to the power 4. Okay, now I would retain the multiplication sign, and then I have 2 to the power 3. Okay, so 2 to the power 3 again, I would multiply the base itself with 3 times. So this is nothing but my 2 to the power 3. Now we know that in mathematics, obviously our multiplication is associative and commutative, right? So that is why I have 1, 2, 3, 4 twos multiplied, and then 3 more twos multiplied with itself. So can I write it as, within the same bracket, 2 into 2 into 2 into 2, these 4, and then I'll continue 3 more multiplications, 4, 6, and 7. Now we have 1, 2, 3, 4, 5, 6, 7. So can I say 2 is multiplied with itself 7 times, right? If 2 is multiplied itself with 7 times, can I say this is nothing but 2 to the power 7? Okay. And if you try to understand a relationship here, obviously 4 plus 3 equals to 7. So if you see 2 to the power something into 2 to the power something else, so when you have base same and indices could be same, could be different, doesn't matter. So when the base is same and they are raised to different powers or different indices, they are multiplied together. So the answer is this would be 2 to the power index of this one, first one, plus index of second one. So 4 plus 3, that is nothing but 2 to the power 7. Okay, I repeat, when base is same and it is raised to some index multiplied by same base raised to either same or different index, doesn't matter. So the relationship would be retain the same base and add both the indices. Okay, okay. So we will write just a generalized rule on this. Okay, I'll just give you a moment. You can note it down, and then we'll go into the generalized rule of it. Okay, fair enough. So let's get into the generalized rule. So we have done it that a to the, so let me write it like this, that let me use a as a constant, right? So this rule can be written as a to the power m into a to the power n. So I have is nothing but a to the power m plus n for all m and n belonging to your natural number set, and m may or may not be. M may be equal to n. This is also fine. M may not be equal to n. So there is no restriction for that. So we need not even write this as a condition. So for all m and n belonging to your natural number set, so which would mean that if same base is raised to two different powers, we can add them. And rather, even if they're fractions, still we can do that. So we can say that m and n belonging to your real number set, so when they are raised to different powers, we can just add them. Now, one more, so we can say this is nothing but our sixth law, okay? And one more generalization that we should understand here is, if a to the power m multiplied with a to the power n multiplied with a to the power, say, p multiplied with a to the power q multiplied with a to the power r, okay? Same base raised to five different indices, and I'm multiplying them with each other. So obviously your answer would be a to the power m plus n plus p plus q plus r. So don't think that this addition rule is applicable only when two indices are multiplied. Oh, sorry, I mean two exponential numbers are multiplied with each other. It is equally applicable if n number of exponential numbers are multiplied with each other as well. Okay, so yeah, you can just take a note of it, and in the meanwhile I would start creating more white space for me. Okay, so this is your rule number 6. Now let us go to the next part of it. So we will first we saw the your 5 basic rules, then we saw how do we use the addition part. Now let's see how we will use the subtraction part. Okay, now let us use the similar thing, right? So uh, 2 to the power 4 divided by 2 to the power 3. Note here that here base are same, and you have two different indices. They can be same, they could be different, no worries. So let us follow our rule number 1. Anything to the power, any positive number is nothing but that multiplied with itself that many times. So I 2 to the power 4, I multiplied 2 with itself 4 times, divided by 2 to the power 3. So 2 into 2 into 2, 3 times. 4 times in the numerator, 3 times in the denominator. So obviously these two cancels out, these two cancels out, these two cancels out. What I get is nothing but 2. Now, we know from our rule number 2 that a to the power 1 is nothing but a. So 2 is nothing but I can say 2 to the power 1. And here, if you notice, this one is nothing but 2 to the power 4 minus 3. 4 minus 3 is 1, right? So when you have a particular base raised to one index divided by the same base. So if it were suppose 3 to the power 3, you cannot do this operation. So base must be same. 2 to the power 4 by 2 to the power 3 is nothing but 2 to the power 4 minus 3. Okay, so we can write it down as a generic rule again. We can write it down as a generic rule again. That is a to the power m divided by a to the power n is nothing but a to the power m minus n. Probably you can say this as your rule number 7. Okay, okay, fair enough. Now you can say that, sir, what would be the value of a to the power m by a to the power n by a to the power p by a to the power q? One simple thing, when you have multiple divisions, it is important that whether your equal to sign is here or here or here. So based on that, solve it so that you would finally get something to the power something. I mean, say x to the power y by, if you are getting x to the power q, then you can say x to the power y minus q. Okay, that is how we solve when it is having multiple divisions. So that is where your having the equal to sign in the right place is very important, right? So yeah, that is how we will solve it. Now let us move on to the next relationship related to this. Okay, now let us get into the multiplication. Okay, and let us see what that would be. So say if I have 2 to the power 4, right, to the power 3, to the power 3, right? So let us try to solve it. So 2 to the power 4, let us first try to solve what is inside the bracket. That is nothing but 2 into 2 into 2 into 2. So it is 4 times. So I have resolved 2 to the power 4. I will retain the power 3 like that only. Okay. Now I will again apply my law number 1 to this thing. So something to the power a positive integer is nothing but this thing, that is 2 into 2 into 2 into 2 4 times. I need to multiply this entire thing with itself 3 times. So this is what it would be: 2 into 2 into 2 into 2. Keep multiplying. So we need to understand what it is. So don't think, and again, students, don't think that these are very silly steps. We are going really slow. Always remember, the fastest computer that you see in the world knows only two things: 1 and 0. The only difference is it understands the core of it, and it recursively uses that so fast that it becomes the fastest supercomputer. So let's understand the base that would help you run very fast over a period of time. Now, why did we do it? So if you notice here, now again using that associative and commutative property, can I just remove these brackets and just directly put a multiplications here? And now if I count how many twos I have: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Very good. So this is nothing but 2 to the power 12, right? So what did we understand? So 2 to the power 4 whole to the power 3 is nothing but 2 to the power 4 into 3. Okay. And this can be written again as the next law, that is a to the power m whole to the power n is nothing but a to the power m into n. So this one probably you can write it as your rule number 8. A to the power m to the power n is nothing but a to the power mn. Okay, okay. Now let us move a little further. We'll understand two more laws, and then we will take a logical pause in our today's class. Okay, so let us go into the next relationship. Now, this is a little different. So, suppose we had 2 to the, suppose we had seen 2 to the power 4 by 2 to the power 3. Okay, now suppose if I had if I had 2 by 3 to the power 4, right? So rather than having the same base raised to a particular index by something else. If I am 2 by 4 to the power 3, then obviously this would be 2 to the power 4 by 2 to the power 3, right? So a by b to the power m is nothing but a to the power m by b to the power m. Okay? Yeah. And you can write it down as your rule number 9. And again, you can define it in the same way. So 2 by 3 raised to the power 4 is nothing but 2 by 3 into 2 by 3 into 2 by 3 into 2 by 3, right? So this can again be rewritten as, you can take all the four numerators together, 2 into 2 into 2 into 2 divided by 3 into 3 into 3 into 3. Again, using your law 1, this numerator is nothing but 2 to the power 4 and denominator is nothing but 3 to the power 4. So that's why a by b whole to the power m is nothing but a to the power m and b to the power n, right? So, for example, we took it here 2 to the power 3 into that. This is how it would be resolved. Okay, and again, we will use all these, to solve problems on indices. Okay, so yeah. Now let me move on to the next relationship. That is another form related to your multiplication. Okay, and that is a b multiplied and whole to the power m is nothing but a to the power m into b to the power m. Okay, and again let us see the proof of it. Suppose I want to have 2 into 3 to the power 4, right? 2 into 3 to the power 4. So can I say this is nothing but, let us use law 1, anything raised to a positive integer, 2 into 3, 2 into 3, 2 into 3, 2 into 3, 4 times. So I repeated 2 into 3 4 times. Obviously, that is nothing but 2 into 3 whole to the power 4. Now, again using the associative and commutative property, I can take all two together. So I have 1, 2, 3, 4, 4 twos. 1, 2, 3, and 4. All four twos, they came together. Similarly, I have 1, 2, 3, and 4. 4 threes. So 3 into 3 into 3 into 3. Again, using your law 1, your 2, this can be written as 2 to the power 4 in exponential, your thing. And then this can be written as 3 to the power 4, right? So this can be rewritten as 2 to the power 4 plus 4, right? Right? Absolutely wrong. So this law is applicable only when your base is same. So here base is 2, here base is 3. So obviously I cannot use this, right? So this is wrong. So this is where it ends. So this is the last step. Obviously we can compute what is the value of 2 to the power 4, that is 16. We can compute the value of 3 to the power 4, that is nothing but 81. Then we can compute it and write down what will we get as the final answer. That is fine, but never do it as 2 plus 3. Or some people, what do they do? 2 plus 3 is 5, 5 to the power 4. No, don't invent new relationships which are not there, defined by the mathematicians. Okay, so yes, so just note it down and then we will go to the next relationship. Okay, okay, very good. Now let us go into the next one, and that is where we would end our today's class. So, and that particular thing we would use extensively in our problem solving on indices in our next lecture. That is when we have a to the power b equals to, suppose, a to the power c, then obviously either this implies either b equals to c for all a not equal to 0 or 1, because when it is 0 or 1, as per rule number 2 and 3, there would be different values. But suppose I have 3 to the power 2x equal to 3 to the power 12. So obviously that would mean your 2x equals to 12. So when while solving it, I should solve it as 2x equal to 12. So that obviously means x equals to 12 by 2, that is nothing but 6. So we would use these property, many often in our next lecture, when we will see how to solve, the curated practice problems on indices and exponential functions. So hope you enjoyed our today's lecture. Meet you soon in the next one. Thank you. Till then, have a good time. Bye bye.